The topic that I'll cover in this video is degrees of freedom, and how we calculate our degrees of freedom for a given system is that our number of degrees of freedom is equal to our number of unknowns minus our number of independent equations. And if our degrees of freedom are greater than 0, then we have more unknowns than we have independent equations, and so this is not solvable. We need more information. If our degrees of freedom is equal to 0, we have one solution. And if our degrees of freedom are less than 0, that means our number of independent equations, our number of equations that we can use to solve, is more than our number of unknowns. Then we have multiple solutions. And those solutions may be the same, so we may have consistent information, or those solutions may not be the same. We may have inconsistent information, and a lot of times we have, in real processes that we see, we have multiple solutions because we're measuring various data points to kind of cross-correlate them. Now here, what we mean by independent equations is a variety of things that we might classify as independent equations. One is material balances, one for each molecular species, and we use, the textbook uses this notation NMS in the Felder textbook. Process specifications, which are usually something that's given, so they might say in a problem 70% of a certain flow goes into a certain stream. In this case, 40% of a flow of stream 1 goes into stream 2. Physical properties and laws are other independent equations that we might include, and so that might be knowing a mass flow from a volumetric flow based on specific gravity or density that we might know. One other is physical constraints, so mole fractions adding up to 1. And some others that we'll consider later in the course are stoichiometric relations and energy balances for each unit. So we're going to take an example here and do a degrees of freedom calculation on this example. And I've got an extractor here, and what I'm taking in are olives and olive oil, and creating olive oil and solids. And these olives are composed of let's just say oil, O, and solids, which we'll call S. So here I have a kilogram a second coming in. I don't know what the weight fraction of either oil or solids is in that kilogram per second. And I have some mass flows of oil coming out and solids coming out, and those are split perfectly. So I only have oil in this stream number 2, and I only have solids in this stream number 3. So here, if I look, my number of unknowns is going to be 4, and I'll highlight these in red. So I have the weight of oil, I don't know. The weight of solid, I don't know. The mass flow of oil, I don't know. And the solid flow as well, I don't know in that stream 3. So I have those 4 unknowns that are listed up there. My number of, I guess, independent equations, this I'm going to split up based on what we see up here. And so I have 2 material balances. That's on oil and on solids. And then I also have one I'll add one to those. Physical constraint. And this physical constraint is that the weight fraction of oil plus the weight fraction of solid is going to be equal to 1. So here, what I'm going to find is that my degrees of freedom are going to be 4 minus 2 minus 1 equal to 1. And if we look back at our definition for degrees of freedom, we see that if they're greater than 0, the system is not solvable. And if we look back down at this system, we can see that we need one more piece of information to solve this system. So for example, if I got the weight fraction of solids here in stream 1, so that was, let's say it was 0.9, right? I would then be able to use this physical constraint equation. I would find out that this here is 0.1, right? 1 minus 0.9. I would then be able to use either of my material balances, and I could find that the mass of oil and the mass of solids.